So you've heard me mention in previous videos the integral test several times. Well, I can finally now say this is the video where I'm going to talk about the integral test and what it is. This is another test for absolute convergence. Similar to the direct comparison test, incredibly powerful. But you have to be sure you're following the hypothesis. It's a very common mistake that students use this when you actually can't. So the series I'm looking at, the terms have to be non-negative and decreasing. So it's very hard for us to use this test for anything like to put the absolute values because of how it works. Basically, if you see you're going to have negative terms, you just can't use the integral test. The trick of putting it in the absolute value like we do with ratio test or with limit comparison test, it just doesn't work. So the idea of this is, if I have a series where all of the terms I'm adding up are non-negative and decreasing, then my series will converge if the improper integral converges, and my series will diverge if the improper integral diverges. So just a reminder, incredibly powerful, but you have to be sure you're following the hypothesis. Non-negative terms and decreasing. Secondly, the value you get for the integral is rarely what the series converges to. This doesn't tell us what the series is converging to, it just tells us whether it converges. So as long as I get a real number for the improper integral, the series would converge. No idea what it converges to, just that it converges. So an example of this. If I look at the series where n is going from 1 to infinity of 1 over n squared root of n. Radicals are not our friends, so I'm going to change this to be the series as n is going from 1 to infinity of 1 over n to the 3/2. This is technically a p-series, but if you remember, I said the p-series is a special case of the integral test. So I'm going to actually go through the integral test so you can see how the p-series is just this, just faster. So 1 over n to the 3/2 is always going to be positive, which is good. And as n gets bigger, I also know that 1 over n to the 3/2 is decreasing. I need this part to show I'm allowed to do the integral test. Remember, I don't have to say the names of the test I'm doing as long as I'm showing that show my work of what I'm doing. In other words, I address the hypotheses, much like with our EVT and MVT, etc. So this means I'm going to look at the integral from 1 to infinity of 1 over n to the 3/2 dn. If that integral converges, my series will converge. And I can already tell because of the p-series test, it should converge. It's kind of nice to be able to peek ahead on my answer. The constant on the bottom, it really could be any constant that's within the domain. Like I could not start at 0 because 0 would not be in the domain of 1 over n to the 3/2. Typically, whatever n starts at in our series is what most people put as the lower bound. So it's okay. Since my n started at 1, I stuck a 1. But it could really start at anything within the domain. So this is the integral from 1 to infinity of n to the negative 3/2 dn. Infinity is not a real number, so I need to replace it and say I'm going to do the limit as b goes to infinity of the integral from 1 to b of n to the negative 3/2 dn. Remember, evaluate the integral, then worry about the limit. So I'm just holding on to my limit here. Antiderivative of n to the negative 3/2 would be negative 2 n to the negative 1/2, evaluating from 1 to b. Still haven't finished my integral, so limit's still there. Plugging in b, I'd have negative 2 over the square root of b. Plugging in 1, it'd be -2, so it becomes a +2. I'm done with the integral. Now I can work on evaluating the limit. So as b is going to infinity, -2 over the square root of b is getting smaller and smaller and smaller. That's approaching 0. So this limit is approaching 2. Because this integral converges, that means my series also converges by the integral test. P-series are common. That's why we kind of just do its own special case of this. But the integral test, incredibly, incredibly powerful. It's a really nice test to be able to work with. And the reason why you needed to cover improper integrals prior to learning how to do this test.